Hi, we are in module 52. Module 52 is about multipliers and other arithmetic circuits. So, we will start with multiplication. So, if you go and look at any processor typically has what is called an arithmetic and logic unit. An arithmetic and logic unit does all kinds of arithmetic calculations. So, arithmetic operations include addition, subtraction, multiplication, division, and things like comparison and whatnot. And you may also have logical operations like logical AND or bitwise OR, things like that are all done by ALUs. So, the operations to be performed are usually given by a control circuit. So, based on the program that you have, you may have operations which say now add these two numbers, subtract these two numbers and so on. Typically, you design them using what is called a bit slice fashion. A bit slice fashion is for an ALU is one in which you design the circuit for one stage and you just copy that for all the other stages and that gives you the whole design. For example, when we did ripple carry adder, just the full adder is a slice. So, that is a single slice and I put various slices together and I get the whole circuit. So, think in terms of bread. When you cut bread, you get slices, but when you put the slices together, you get a loaf, right? You can think that it is the same analogy. When you put the bit slices together, you get the whole circuit. And we looked at carry, look ahead and ripple carry and so on. All of them have some kind of repetition. It is not that the circuit looks random. There was a very nice and repeatable structure that you will see in many of the circuits. So, we will look at multiplication here and we will see how to do that in a very structured manner. So, we have what is called the multiplicand and multiplier. We have two numbers, multiplicand and multiplier. So, multiplicand is the number to be multiplied with and multiplier is the number that we are multiplying. So, in the previous video I said subtrahend and minuend. I think I mixed up what is subtrahend and what is minuend. So, it is the other way around. So, minuend is this and subtrahend is what is getting subtracted from and minuend is what you are subtracting. If you do A minus B, A is subtrahend and B is minuend. So, I think I mixed it in the previous video. So, anyway, well, let us look at multiplicand and multiplier. Multiplicand is what you are multiplying to and multiplier is what you are multiplying with. Now, if you want to do grade school multiplication, so grade school multiplication is how you do it in your second standard or third standard. This is how you do it, right? If you are given two numbers, you will take the last digit of the multiplier, multiply with all the digits of the multiplicand, have it written down. Then you will take the second bit, multiply with all the digits, write it down, but you will shift it by one position. Then the third one you will shift it by another position, fourth one you will shift it by another position and so on. So, we will call these the individual bits are called partial products and this whole thing is called a partial product array. So, we have an array of partial products and once you have an array of partial products, what you have to do is you will do column wise addition, right? You will take 0, so that is 0 itself, 1 plus 0 is 1, 0 plus 1 plus 0 is 1, 1 plus all zeros is 1, then 1 plus 1 is 0 carry over 1, 1 plus 1 is 0 carry over 1, 1 plus 1 is 1 carry over 1, then 1 plus 0 is 1 and 1 itself. So, this is the product of these two numbers here. So, I believe this is 10 plus 32, that is 42, 42 into 11 I think. So, we have this into this gives me this result, right. Okay. Now, in general I can write x which is the, so let us say I want to multiply two numbers m and n, so two numbers x and y, let us say x is a m bit number and y is a n bit number, then the value of x is I equals 0 to m minus 1 xi 2 power I. This is an unsigned number, so it is a positional representation and this is what we have. For y again it is a positional representation and that is what we have. The product p which is x times y is sigma of pk into 2 power k, where pk is the partial product. So, that is the partial product that you are getting multiplied by 2 power k. So, if you want to expand it, it eventually actually is a double summation. So, I equal to 0 to m minus 1, j equal to 0 to n minus 1 xi yj into 2 power I plus j. So, all this is saying is you are taking the bit xi has a weight of 2 power I, yj has a weight of 2 power j, When you multiply that together, you get xi yj and with a weight of 2 power I plus j. So the overall value that you have for the product is essentially take all the bits and multiply with each other, but with appropriate weights that is taken care of. So let us do this on a piece of paper for decimal numbers just to make it clear. So let us do this small example and I will show you how to understand this using regular multiplication. So let us say I want to do 49 times 12. So what I am going to do is, in the grade school multiplication you do this, 2 times 49 is 98, 1 times 49 is 49, and you add it together, the result must be 588. This is what I want. The partial product interpretation says take each and every location, multiply with each and every digit with the appropriate weights. So if I look at 49, I can think about it as 4 into 10 power 1 and 9 into 10 power 0. 12 is 1 into 10 power 1 and 2 into 10 power 0. So the actual weights are like that, right? And this is what I am multiplying. So I am going to multiply each of these pairs together. So the overall product P is, I will take one pair at a time from, so one element at a time from the top, one from the bottom, and for all the 4 pairs I have to sum it up together. So let me take this one first, 4 into 10 power 1 times 1 into 10 power 1. So the result is 400, right, plus, then let us say I do these two together now, 4 into 10 power 1 times 2 into 10 power 0, that is 80, right. Then I am going to add, let us say these two I will multiply together, that is 1 into, so 9 into 10 power 0 times 1 into 10 power 1, so that is 9 into 1 into 10, that is 90. Finally, these two together, that is 9 into 10 power 0 times 2 times 10 power 0, so that is 18. You add all of that together, that is 400 plus 170 plus 18, the result is 588. So it is hopefully clear that what this product, let us get back to the slide, you will see that all we have done is we have taken each and every location xi and yj, we have multiplied the bits together instead of the digits, and the weights are not 10 power something, it is 2 power something, and the weights are weight of I and weight of j together. That is all we have. It is fairly straightforward, and we are going to generate a circuit which mimics this idea. So what we are going to do is we are going to do something called an array multiplier. The first thing you have to realize is getting these partial products is actually fairly easy. Here we are not looking at digits, we are only looking at bits. So if I take this bit 1 here, that is in the multiplier bit, if I multiply with this one, it is fairly straightforward. What you have is either we copy this thing directly, so if it is a 1, the multiplicand is there as it is, if it is a 0, it is a series of zeros, right, and multiplying with a single bit is essentially equivalent to ANDing, right. If I want to AND 2 bits together, that is equivalent to multiplication of the 2 bits. So A and B is the same as A multiplied by B as long as A and B are single bit values. So what I am going to do is, I am going to take, let us say x3, x2, x1, x0, that is a 4 bit number to which I am multiplying with y0 to wherever, right. So if I take y0, that is in the row here, and in the column I give x3, x2, x1 and x0, this is one of the partial products. So this is the multiplier bit y0 multiplied with the multiplicand x3, x2, x1, x0. So the first partial products will be coming out of these AND gates here. The interesting thing is P0 can be looked at as just x0 into y0, you do not need any more calculations. Now let us look at the next stage. You look at y1, you take y1, multiply with x0, x1, x2 and x3, right. You multiply all of it together, this is the same as taking the second rightmost digit and multiplying with the multiplicand, and when you do that, that is giving you, so that multiplication is again just a sequence of ANDs. But now what you are going to do is, we are going to do something slightly different. So now we have two numbers and we have shifted them appropriately, we need to add these two together, right. So that is the addition that is done here. So, if you notice here, this is x1 y0 plus x1 y1 added together, and that will be P1. You can go and look at this circuit here. If you look at P1, it came from this and this product and this product. What is this product? It was this bit into this bit, and this one is this bit into that bit, right. So, you can see that if I go and look at what is coming out of the half adder, the sum, it is, you look at this one, it is x1 and y0, and this one is x0 and y1, that gives me P1. So, that is P1. You continue doing this for each and every step. So, the very first stage is just AND gates. In every partial product stage, it's, so if you put this circuit here, half adder, full adder, and half adder. So, essentially what you are having is, so I guess this must also be a full adder. So, that is a mistake here. I guess this is, okay, this is not a full adder. So, it is only a half adder. So, this is fine. So, what we have is, if you do the circuit here, then it is taking partial products which are coming from two levels, adding them together, generating the sum, and that sum can be added with the next partial product array, that will give you the next sum and so on. You do that for 4 steps, y0, y1, y2, y3. At the end of it, what you will get is the final product. So, I hope that this is clear to you. What this one is giving is the first partial product. This one, this AND always gives the partial products, and the adder, that is after that, adds up two partial products together and gives the sum, and that sum is again ANDed with the next partial product array, that gives you the next partial sum and so on. So, the various partial products, you can add them one at a time and you can get the final result also. So, this is called an array multiplier. The reason why it is called an array multiplier is, first of all, it is doing multiplication, it is taking two numbers and multiplying them together, and it is called array multiplication because we can do all these things. So, you can see that there is a nice regular structure to the whole thing. If I want another, let us say I want to have x3 to x0 multiplied with y0 to y4, all I have to do is take this final stage that is out there and copy it once more, and this will work. So, you can see that the whole thing is a nice bit sliced kind of structure. At every location, you have an AND gate and a full adder, except for the very last stage where it is half adders. So, this is a very nice and interesting circuit that you can replicate very, very easily. And so, if you want to do this as a circuit, what we have is, we have some m bit value, in this case it is 4, we are multiplying with another n bit value, also here n is 4, the result is a m plus n bit value, in this case it is 7. So, let us look at, in general, let us say there is a m bit value multiplied with an n bit value, then if you want to look at the performance of this array multiplier, so let us see how to calculate the performance. There are lots of things here, right? The whole thing is combinational. We want to see what is the worst case delay that we have because of this. So, if I go and look at this path, you go and look at this path, a change here may have to go through this half adder and a full adder, then one half adder and a full adder, and if there are more and more steps, one half adder, full adder and so on, it will come as though it is like a stair, it is like one step at a time. In the very last step, it will be this carry that is coming out of here may have to ripple all the way through to the leftmost side. So, that is a long path in the circuit, right. This is a long path, it is starting from the last bit and goes all the way to the very first bit, right, the leftmost bit. So, this is one of the critical paths, and there is another path which is also quite long. So, what happens here in this one is, you go down on this and there is a carry that is coming from this stage itself, right. So, this stage is the addition that you are doing for the first partial product with the second partial product. That adder itself may have a delay, and once that settles down, it will then go down like a staircase. So, essentially it is either go down a staircase and then go all the way to the left, or go all the way to the left and then go down a staircase. These two are critical paths, and the worst case delay happens to be T of AND, which is the delay of this AND gate itself. So, there is one AND gate here, the delay of the AND gate itself is there, along with m minus 1 plus n minus 2 times carry plus n minus 1 times T sum. So, this T carry is the delay required for generating carry in the full adder, and T sum is the delay required for carrying the sum bit. So, every time you go down, that is for the sum bit, every time you go to the left, that is because of the carry bit. So, you can calculate the number of steps, wherever it is green you calculate the number of steps. So, I am sorry, wherever you go from left to right, that will give you T carry, and wherever you go from top to down, that is because of sum. You add all of it together, you will see that there is m minus 1 plus n minus 2 times carry plus n minus 1 times T sum. So, this is, you can see that the multiplication of two numbers m and n is actually not of the complexity m times n, the complexity is m plus n, right. So, that is a very interesting thing. The array multiplication, right, is taking a number of steps which is not m times n, because you can generate the partial products in parallel and you can add numbers together. The array multiplication does not require mn steps, it requires order of m plus n steps. If you want to do signed multiplication, so let us take a simple example. Let us say I want to do a positive multiplicand with another positive multiplicand, there is nothing which is different. So, this is what you would have done in the array multiplier anyway, right. You would have generated partial products for each one and you would have added them. If it is a positive, if the multiplicand is positive, which means, so you are doing x times y, if x is positive, then all you have to do is in each of these locations prefix a 0, right. It is a positive multiplicand, so you prefix a 0 together and you add all of this together, that result will be correct. So, again you can go back and verify this. If it is a negative multiplicand, however, so in this case again we are assuming that the multiplier is positive. So, if the multiplier is positive, the multiplicand is negative, you generate the partial products as before, but you do not add them directly. Instead, you go and sign extend each of the partial products. So, this partial product is 10010, you sign extend it. For a signed number, extension means take the most significant bit and copy it till the leftmost one. So, here again the most significant bit is a 1, you copy it to the leftmost, this is a 0, so copy it to the leftmost and so on. You add it together and you interpret that as a signed number, you will realize that it is the correct interpretation. In this case, this number, so this minus 14 is actually in 2's complement. So, this is not signed magnitude, it is 2's complement interpretation, and the 2's complement multiplication can be done in this way. So, this is plus 11 in 2's complement, this is minus 14 in 2's complement, the result you get is minus 154 in 2's complement. So, of course, if you have a negative multiplier, you have a problem. So, this array multiplier idea works only if the multiplier is positive, the multiplicand could be positive or negative with the sign extension. However, in the negative, if the multiplier is negative, so if I want to do something like a times minus b, instead treat it as minus a times b. So, you negate the multiplier first and also the multiplicand, you negate both of them and use the same scheme, it should be one of these things then, right. If I want a times minus b, then where b is a positive number, I want to do a times minus b, instead do it as minus a times b. Now, minus a could be positive or negative, and minus a you could use either this or this circuit. So, negation of the multiplier, so negative multiplier is not a problem, it is only a special case for the previous case that we have discussed so far. You can also do what is called modular multiplication. Instead of doing a bitwise thing, you can also do something called modular multiplication. You can take a group of bits at a time and multiply them together. So, you have, let us say I have built an array multiplier which can take two 4-bit values, just that, it can take two 4-bit values and multiply. If I want to build a 8x8 multiplier, I can do this, supply the lower half of a and lower half of b, get it multiplied, store the result. Then you look at the lower half of b and upper half of a and store the result and so on. So, you can do something in a very modular way. So, you can calculate complete, so instead of looking at bitwise things, you can take a nibble at a time or word at a time and so on, and you can group them together and multiply it, and finally add them together. So this is called modular multiplication. So the modular multiplication would work like this. In the first round, you use a 4 by 4 multiplier, get A30 times B30. In the second round, you use the same 4 by 4 multiplier, but you get A74 and B30 multiplied. And once this is over, you can get these two added up. Meanwhile, you can use the 4 by 4 multiplier to generate A30 and B74. And once that is calculated, you can use an adder to add this with the top two. Meanwhile, you can generate A74 and B74. Once that is also ready, you add it with these three partial arrays, the final result will be there. So that's one way to do it. The other way to do that is you generate all of them using 4 by 4 multipliers. In fact, if you use 4 parallel 4 by 4 multipliers instead of the same multiplier many times, you can also use separate 4 by 4 multipliers, and whatever you have, right, you can add it vertically with this alignment. So in this case, in the worst case, you have to add 3 numbers together. So this is a number that's directly coming in, this is a partial product that will directly come in, but here we are adding 3 numbers and here we are adding 3 numbers together. If we build a circuit that can do this, then we can do what is called modular multiplication. So I will show you how to add 3 numbers together in the next slide. So essentially what we have done is, we can conveniently do this as, first do A30 and B74, then we do these two together and then do this together and add them together. So adding 3 numbers can be done like this. If I have numbers, let's say x, y, z, and if each of them is a 4-bit number, if I want to add these 3 numbers together, then so you take the full adder, instead of giving the carry here, give the z's, z3, z2, z1 and z0, you give those. That will give you sums and carries, right? So there is a sum and there is a carry, there is a sum and there is a carry, there is a sum and there is a carry, and so on. Have another array of full adders where you take sum from the previous stage and carry from the next stage, add it together, and the carry in should come from the rightmost side. So this is the first level of full adders, this is the second level of full adders. So we are not reusing the full adders, we are actually having a circuit which has 7 full adders here. So if you put this circuit in 2 steps, in 2 full adder delays, we can add 3 numbers. So instead of one complete ripple carry and whatnot, we have used 2 full adder delays, and with that you can actually get addition done. So 1 plus 3 is 4, actually you need 4 full adder delays in the worst case. So 3 numbers can be added together, instead of incurring a ripple carry of n minus 1 plus another ripple carry of n minus 1, we can actually do it in 4 steps here. So now let's move on to other circuits. So comparator is a circuit which looks at 2 numbers x and y which are of the same width and tells you whether they are equal or not. So the way to do that is, you start from the rightmost one. Let's assume that initially the numbers are equal. We will assume that the numbers are equal till we get a condition where the numbers are not equal. What we will do is, we will start with I equals to 0 and we are going to run a repetitive algorithm. We will see how to design hardware for this later. If xi equals yi and if eqi is equal to 1, which means everything to the right side seems to be the same and xi and yi are also matching together. So you are looking at a location I, xi and yi are the same and everything to the right of that were also the same. So at this location, you still know that they are only the same. So eqi plus 1 is 1. However, from the right side, if they are not the same, even if the current bit is the same, then they are not the same. So let's look at an example here. So I'll take numbers instead of bits. Let's say I'm going to compare these 2 numbers. Let's say this is a number x and this is a number y, and I'm going to look at location I. Right? I can say that without looking at, so I don't know what is going to happen on the left side. I look at positions here and here. If these 2 are the same, then I can say that this number is equal to this number only if everything to the right side were also a match, right? So if EQ of I is 1, EQ of I is, or all the digits from I to later, I minus 1 all the way down to 0, if they are all equal, then it's 1, and if the current positions are also the same, then I can say that so far the numbers are the same. However, if I have a condition like this, let us say 9875 and I get 8875. Up till here things were same, at this location things are different. So, which means to the left side I should say that the numbers are not equal, or I got something like this 99, in this location it is the same, but in some other location it was not the same. So, here it was not the same. So, to the right side is not the same, here it is the same. Either case this number is not the same as this number. That is what a comparator does. So, that is what you see in the algorithm here. Let us look at the algorithm once more. If xi is yi and eqi is equal to 1, for the next stage I can say that these two are still equal, otherwise I will say that they are not equal. And if I is less than n, go to step 2 and do this until all the i's are exhausted. So, for one stage I can look at whether xi and yi are the same by putting in an XNOR gate. So, if both are 0, this is a 1, if both are 1, this is a 1, which means at this stage these bits are equal. I have to wait for something from the right side, that is eqi, and if xi and yi are the same and if eqi is also 1, then eqi plus 1 is 1. So, this is a bit slice of a circuit that does one stage comparison. If you want n numbers or n bits to be compared, I have to put them back to back. So, let us look at this example. I will put eq not equal to 1, I will put 1 here, because this is the very first, this is the least significant bit. So, I do not have anything from the right side, I will put that as a 1, and x naught and y naught will be compared with each other. If they both are the same, then eq1 will be 1, if they both are different, eq1 will be 0. So, all we have done is we have taken the same bit slice and repeated it again and again, we just connected it. There are no logical blocks connecting them. That is the interesting thing about a bit slice circuit. In a bit slice circuit, all you are doing is connecting the wires together without requiring extra gates. So, if I did this bit slice here, all I have to do is connect them together properly, and if I go and inspect eqn, it will tell me whether the numbers are equal or not. So, this is a circuit which we can use for comparing unsigned numbers. So, if there are unsigned numbers, I can compare using this. So, a 4-bit comparator is a more general circuit. This general circuit actually can give you 3 outputs, whether A is less than B, A is equal to B, or A is greater than B. This is something that you did in your Verilog assignment also. So, probably you did it in a very different way, but here I am showing you how to do it in a structural way. So, if I have 2 4-bit numbers A and B and I want to compare them, so and these will be the 3 bits. So, A less than B, A equal to B, and A greater than B. Remember that only one of them will be on at any condition, right? It is not going to be different things. Exactly one of these output bits will be on. Let us assume that these 3 we can ignore right now. Let us assume that these are 3 extra inputs that we have taken in, and let us ignore it just for a while now. So, if I want to check whether A is greater than B, then either A30 should be greater than B30, or A30 was equal to B30, and otherwise from the input A was greater than B. So, this I am designing a 4-bit comparator for a slice. This 4-bit comparator may sit somewhere in the middle in a very large comparator. So, all I am putting is a condition whereby if I know something from the right side, how do I tell the left side whether they are equal or same or different, right? So, what I am going to do is A greater than B is true, A greater than B out is true if A30 is actually greater than B30, because this stage if you decide this, I can look at a group of digits together, right. So, even in the example I showed earlier, instead of looking at 9 and 9, I could have looked at 9, 8 and 9, 8 together and compared it. If I designed a circuit for that, that is what this one is doing. A30 is either greater than B30, or these 4 bits are the same, and the current stage I looked at 4 bits, they are the same, but the right side is saying that A was greater than B. If that happens, then A greater than B out is true. So, these are single bit values. Similarly, A equal to B is true only if the current stages say that all the bits are same, and the right side also says all the bits were same so far. A less than B is true if either the current one is, either A in the current stage is less than B in the current stage for this slice, or in the current slice A and B are equal, however you got A less than B from the previous stage. So these are the logical equations. If you expand it, you will get these Boolean equations. I suggest that you go and interpret this whole thing in English, right. So there is a complicated equation here, but I suggest you go and understand this in English to see whether it actually means the same thing as given here. So I explained it in English. I said for the 4 bits, if I know that these 4 bits are greater than those 4 bits, or these 4 bits are equal to these 4 bits, however from the right side I get something greater and so on. So for each of these are the 4 equations. So for given 4 bits, A30 is greater than B30 can be derived using this equation, equality is using this equation, and less than is using this equation. I suggest that you go and understand it carefully. Now if I have a 4-bit comparator, I can design a 12-bit comparator as a bit slice circuit. What I will do is, I will take 3 4-bit comparators, put them one after the other. I will give 11 to 8 of both x and y to the leftmost comparator, then 7 to 4 to the next one, and 3 to 0 of both the inputs to the last one. And I take the less than output from there and connect it to less than input of this, equality in output of that to equality input of this, and so on. That is for all these 3. For the last stage, since this is the last stage, A is, so I cannot say that x is greater than y or x is less than y. I can start with the ground truth that x is equal to y until it is proven otherwise. So I cannot start with a 0 0 0, so you have to be careful, you have to put a 1 here, and we will assume that if there are 0 bits, x and y are same. Now you get 4 bits, x and y could be greater or lesser or equal, and then you have 4 more bits, again x and y could be greater or lesser or equal, and so on. At the end you have x less, so these 3 bits, x less than y, x equal to y, and x greater than y, exactly one of them will be on, and this is again a nice bit slice circuit. Then I want to show you another circuit called the min-max circuit. A min-max circuit is one which takes 2 inputs x and y, and it takes a control signal called min-max. The output z will be equal to minimum of x comma y if min-max is 1, it will be equal to maximum of x comma y if min-max is 0. So to design a circuit like this, you could do this. So min-max is a control input, I give x and y together, and I get a single bit called x greater than y. So this will tell me whether, so if x is greater than y, this is 1, if either x is equal to y or if x is less than y, let us say this is a 0. Then I can give this to a multiplexer, I can give both the inputs to the multiplexer. So min-max should either pick x or y, right, even though it is either minimum or maximum, either way it is either x or y that is going to the output. So I will give that with this extra condition. So let us look at the equations here. X is greater than y is 0, which means x is actually less than y, and I want the minimum, right, min-max says it is 0. So x is greater than y is 0, which means x is less than y, and min-max is 0. So if min-max is 0, I want the maximum, so the maximum should be y. So the select input must be 1, I have to select 1 because of that. If x is greater than y is 0, which means x is less than y, and min-max is 1, min-max is 1 means I want minimum. So the minimum of x comma y should then be x, I want x. To select x, then I must put the select line must be a 0. So if you do this based on the comparator's output and the min-max control input, you will see that this is an XOR, S is an XOR of these 2 bits, x greater than y and min-max bits. So that is why it is an XOR gate. So the XOR gate takes care of the fact that if they both are even equal, the min-max will pick only one of them, right, and either one is fine. However, if x is less than y and you ask for the minimum, then this will be 1 and x greater than y will be a 0. So 1 XNOR 0 will be a 0, so it will pick x, and so on. So you can go and verify for all the 4 conditions that this in fact works. So this brings me to the end of module 52. In fact, this is the logical end of the course. All the course material is done with this lecture. So, in this week we saw several things. We started with number representation, we started with signed representation, namely 1's complement, 2's complement, signed magnitude and excess b, and we looked at arithmetic involving signed and unsigned numbers. So, the essential thing that you have to go with is design a circuit for unsigned operations, and with few modifications you can get it running for signed operations. Specifically for 2's complement, it is fairly easy to do. In fact, that is what you will see in all the circuits, in all the processors and so on. The internal representation is all 2's complement. I also suggest that you go and look at a few PDF files that I will put in the course web page, which has a very nice pictures to talk about where are the different kinds of representations used. Then we looked at adders, namely ripple carry adder and this fast adder called the carry look ahead adder, and we looked at multipliers, namely the array multiplier. So, the array multiplier has time steps which is order of m plus n and not m times n. That is a very useful thing because there is some parallelism that we are exploiting there. Otherwise, we would not get m times, we would not get m plus n. We would have gotten m plus n only if we had done something in parallel. The partial products were all generated in parallel. Because of that, we are able to cut down the number of steps. Finally, in the last module, we looked at comparators and we looked at how to bit slice them together and compare them together and so on. So, this brings me to the end of arithmetic circuits. So, what I have not done is floating point arithmetic. I already mentioned that is slightly beyond the scope of the course. However, I will put the slides related to floating point arithmetic online. If you want to read it, you go and read it yourself. So, this brings me to the end of the course itself, in fact. So, there is one more module, a short video next, which actually wraps up everything that is there in the course. So, I will see you there in the next video.